Thanks, the organizers. So there will be two topics related to my talk. Firstly, I want to talk about the minimal model program in positive characteristic. Secondly, about vanishing theorems in positive characteristic. So let me quickly recall what is known in those fields. So in dimension 2, thanks to work of Tanaka, we know that the minimal model program in positive characteristic works without any problems. And then there is a recent breakthrough result a few years ago for threefolds of characteristic greater than 5 and some other assumptions by Hakon and Shu, and then it was finished off in this general case, but still under the assumption that the characteristic is greater than 5 by Birkar, and then finished off by Birkar and Waldron. And I should also mention an important paper of Cascini, Tanaka, and Shu in this context. So what is a possible next step? So of course you could try to ask what happens when the characteristic is 2, 3, and 5, but somehow we lack any methods of dealing with it. So another possibility is to ask whether we can generalize their techniques to higher dimensions. So we can assume that the dimension is 4, but now the characteristic is very big. So maybe instead of 5, you need to assume 17 or million or something like that, and try to check whether their technique would work in this context. So I would like to talk a bit about that during my talk. As for vanishing theorems, as you probably know, Kodaira vanishing fails in positive characteristic, and there is an example by Mumford of a smooth projective surface that violates Kodaira vanishing, but Kodaira vanishing holds for rational surfaces, rational smooth surfaces. And now it's natural to ask, what about other vanishing theorems? So for example, is it true that Kawamata-Viehweg vanishing holds in this context for smooth rational surfaces? This is unknown. Okay, so the motivation is twofold. Firstly, it's a natural question to ask. I mean, this is the most basic case, so it would be nice to understand whether those vanishing theorems work or not for rational surfaces. Secondly, we are in kind of a stage in the positive characteristic by rational geometry, as far as I understand, that we lack examples. I mean, we still, I don't know, people don't have any idea whether this Hakon and Shu result, and then Birkar and others, it's really an exception, or the minimal model program should work in positive characteristics. So we really need to understand really what's happening on this basic level to see, maybe try to find some examples or counterexamples. Sorry, Paolo. No? No.
The backboard doesn't work.
Oh. Oh, I see. Okay, so maybe.
Yeah, start on the top.
Yeah, okay. That's good to know. Okay, so let me quickly recall basic notions in linear liftability theory. So I assume my field is algebraically closed and is of positive characteristic. And let me recall vaguely what is the ring of Witt vectors, the second Witt vectors. So it's equal to k plus k as a set. So this is just a formal identifier. And multiplication is given by x plus yp times x prime plus y prime p equals to x prime plus x y prime plus x prime y p. So it's like a multiplication even with the property that p squared equals to 0. An example is the second Witt vectors of fp is the same as z over p squared z. So in a certain way, the ring of second Witt vectors is like an infinitesimal thickening of our field fp in mixed characteristics in spec z. Okay, and with that we can define that a scheme X over our field K lifts the second Witt vectors if and only if there exists a flat scheme X tilde flat over spec W2K such that the special point is isomorphic to X. So this W2K, it has 2 points, a generic point and the special point, which is our field K. So in other words, we ask whether this X has a deformation, a second order, first order deformation in the direction of mixed characteristic. So to characteristic 0. And we can also define it for pairs. So we say that a log smooth pair XD, it lifts to second Witt vectors if and only if. I mean, I can say for non-log smooth, but I will use only this in this context. If in addition to the above, we have that for every. So this D is the sum of some irreducible divisors di from 1 to n, and now for every I, there exists a sub-scheme di tilde of X tilde, such that it's the special point. After restricting the special point, it's isomorphic to di. So it's the same idea. We look at xd when you ask whether it deforms in mixed characteristic. And now the important thing is we really want this deformation to be with respect to each irreducible component. So there's no possibility that you have like free curves, free irrational curves, and they deform into an elliptic curve. So that's an important thing. This is usually assumed in this context. Okay, so why do we care? So you have the following theorem celebrated by Deligny-Uzi, and I will present a more general version due to Matsuki Olsen and independently Hara. So what we have is the following. We have X delta log smooth pair over a field K such that it's a KLT pair, so the random of delta is 0. Now we assume some liftability condition. So X support of delta lifts to the second Witt vectors. And thirdly, the characteristic is greater or equal than P. So this is like a technical assumption. But for example, is greater than dimension of X. Greater or equal. And under those assumptions, we get that Kawamata-Viehweg vanishing holds for X delta. So let me maybe say quickly, it means that for every L ample Q Cartier such that Kx plus delta plus L is Cartier, we have that at xi x kx plus delta plus L is equal to 0 for I greater than 0. And we have even more. We have even Nadal type vanishings, but it won't be so important here. In my talk,
So if I don't want Vi to be flat, Vi tilde?
Oh, sorry. Yeah, they are flat over W2K. I mean, in this context, it's equivalent to being smooth over W2K. One can show that. Sorry. Okay, so let me come back to this motivation. So Kawamata-Viehweg vanishing for smooth rational surfaces. So what would be possible ways of attacking this problem? So ways of proving Kawamata-Viehweg vanishing, where we have X delta, and now this is log smooth, this is SNC, and X is smooth rational surface. So the most natural approach would be to try to use Kawamata's covering trick So the idea is the following. We somehow construct a finite cover that ramifies along divisors in the boundary, and then we simplify Kawamata-Viehweg vanishing for x delta to Kodaira vanishing on this finite cover. Now the problem is, even we start with a smooth rational surfaces for which Kodaira vanishing holds, then if we construct this finite cover, it might be of general type. And then we don't know whether Kodaira holds there or not. So in a certain way, I don't know, I think this approach is a bit hopeless, at least from my perspective. Let me mention also that by this theorem, this implies exactly that Kodaira vanishing holds for smooth rational surfaces, because since they are blowups of P2, they all lift to characteristic 0. So it holds from this theorem. And also I should mention, I mean, it's not as obvious as it sounds. I mean, one could say, oh, that's obvious. I mean, I have a pair, it lifts to characteristic 0, so I could use Kawamata vanishing there and reduce it back. But the point is here that we do not assume that this line bundle L lifts to characteristic to the second Witt vectors. So this is slightly stronger. Yeah, that's okay. But I mean, yeah. But there's no even, I mean, even without that, it's still stronger. Okay, second possible way of attacking it, and it was believed that by mathematicians, at least for some time, that it should be true, is to show that x and support of delta, this lifts to the second Witt vectors. Then, by Dolin, Illuzi, Matsuki, Olson, Hara's theorem, this would imply Kawamata-Viehweg vanishing for rational surfaces. But the problem is, it has been proven recently. This is in a recent paper in Duke by Adrian Langer. I mean, among other things, he proves there is that there exists a smooth, rational, projective surface X with an SNC divisor D such that XD does not lift the second Witt vectors. So this approach is also hopeless. Since I think it's a very nice construction, let me just give you a construction, how to construct such a pair, and give you a vague idea why it should not be liftable. So a construction so we take X to be the blow up of P2 defined over FP bar at all FP points. So this is a blow up of P2 at all P square plus P plus 1 FP points. And now we take L1 tilde up to LP square plus P plus 1 tilde to be strict transforms of all P square plus P plus 1 FP lines of P2 on P2. So there is exactly the same number of FP lines as the FP points, and all those lines intersect at those FP points, and we take their strict transforms. And now the point is that they are disjoint, right? Because they only intersect at FP points, and we blow them up. And now Langer claims that X and sum of Li tilde, that this does not lift to the second Witt vectors. So the vague idea is, I mean, his proof depends on some Bogomolov inequalities on Higgs boundaries, so it's pretty complex. But as idea why it should not lift is pretty simple. The point is that if it did lift, it would violate Hiromu's inequalities for line arrangements. So the point is, if it lifts, the incidency of those lines, how they intersect, should be preserved. And we see we have exactly the same number of lines as points. And that's impossible in characteristic 0. I mean, this number of intersection points, especially for such a configuration, would be much, much bigger. So there's a special property of FP, that such an existence of such lines exist. So let me make a small remark. I would like to rephrase it slightly. So all those lines, their self-intersection is minus p minus 1, and so we can contract them. So we can contract I tilde. And then we can rephrase what I just said, that x and the exceptional divisors of pi does not lift. So what I'm just saying, that those curves are not like as arbitrary boundary. In a certain way, they are exceptional divisors of some resolution of some singular surface. I mean, that's maybe looks a bit vague, but I will explain why I need it later in my talk. Are there any questions, maybe? So I would like to move the second part, which are Frobenius splittings. So here I assume that my X is normal variety, defined over an algebraic closed field of positive characteristic. And we have the following definitions. We say that X is globally F-split if and only if the Frobenius morphism, which goes from OX to push forward by Frobenius OX, this splits. And by this I mean that we have the following diagram. We have OX to push forward OX. Here we have, again, identity map to OX. And splitting is equivalent to the existence of map here, such that this diagram commutes. Similarly, we can define global F-regularity. This is slightly more technical, but let me write it. So for every divisor D in X, it's a divisor, there exists exponent e greater than 0, a natural number, such that the following map splits. So this is Fe from OX to E times composed Frobenius OX. And now we make an inclusion into OX of D. And we require that this splits. And one could define it locally, so we'll have that X is locally F-split, locally F-regular, if the above holds for each stock of XX. So I should explain myself. I mean, I don't want to confuse people with notation who hasn't seen those definitions before. And because of that, I might confuse experts in this field. So by locally F-split here, I mean F-pure. And by locally F-regular, I mean strongly F-regular. But I find it clearer, I mean, in this context, to call just it a local notion, since being F-pure is exactly being globally F-split. So this F-splitness, I mean, is kind of an omnipresent notion in algebraic geometry. So before it was kind of studied by rational geometers, has been applied in representation theory, intersection theory, effective commutative algebra, or even derived categories. But somehow it happens, it's a very strong notion, you have a lot of applications of that. But what happens is this notion really comes from birational geometry in a certain sense. So I should also mention that one can define those notions, so this F-splitness, the local and global context, and F-regularity for all log pairs X delta. But then it's far more technical, so please, I mean, forgive me because I omit those definitions, but they are very similar to what I wrote above. Okay, so what to think about this? So what happens is the following. We take local F's, one more thing. And here, whenever I would talk about those notions for pairs, what I really mean, I would mean sharp F-splitness and sharp F-purity. So every time I talk about F-splitness, it is assumed to be sharp. That is, yeah, if somebody has seen it before. So what do we have? We have that local F.
Global F-purity? I don't think there's a notion for sharp F-split.
Sharply globally F-split. I mean, so we define this notion.
It's called globally F-split, and the other is called sharp F-pure.
Oh, really? Anyway, so I assume this round down, upper round down. Yeah, this is it. Yeah. I mean, it doesn't matter because we work in high characteristic, so those notions be the same. But I mean, that's, yeah. It won't be important. Okay, so locally F-split, so this is F-pure. This implies that a singularity, so this is a local notion, it's a notion of singularities. So this implies that variety is log canonical. Now, local F-regularity, I mean strong. Here, somebody have seen it before. This implies KLT. Now, global F-splitness. This implies log Calabi-Yau type. So, as defined before, it says that there exists a so for x, there exists a boundary delta such that minus kx plus delta is trivial, and this pair is log canonical. And global F-regularity implies log Fano type. And what really happens is that those notions are very similar to each other. So in a certain sense, for example, being locally locally F-regular, being that only geometric abstraction for a singularity to be locally F-regular is to be KLT. So in a certain way, local F-regularity is KLT plus some arithmetic of the variety. I mean, that's a very vague statement, but it's more or less the general idea. Maybe I don't want to delve into it more. So, I mean, if you're afraid of those notions, just think of LC, KLT, log Calabi-Yau, log Fano, and say there are some positive features going on there. Okay. So why those notions are nice? Because of the following, so we have the following properties. So, properties. X is globally F-split. This implies that it lifts the second Witt vectors. And this is due to, I mean, it's hard to say thanks to whom, but it's more or less Srinivas, Mehta, Bhargav-Bhatt, and Zdanovic in different contexts. Okay, and now we have a pair X delta globally F-split. Then this implies that Kawamata-Viehweg vanishing holds for X delta. So you can use those Frobenius properties to prove Kawamata-Viehweg vanishing. Okay, what are examples? I mean, I haven't given you any examples. So let us just start with taking a smooth curve.
Can you generalize this property for pairs also?
Liftability.
Liftability,
Yeah. So this is working. I mean, I think it's true, but I cannot give a 100% guarantee. I mean, I talk with some people and they agree with me, but I mean, it sounds a bit suspicious, but I think it's true. So what happens if you have a smooth variety, which is globally F-split, then it leaves to the second Witt vectors together with any SNC boundary, without any assumptions on this being globally F-split. So this is what I believe is true, if it's true. I can give you a proof later, and you can say it's very short.
Yeah, so globally irregular should be any divisor also linked to the bit, right?
Yes. But not even this divisor from the pair. Any other possibly very ample divisor. So this is what I think it's true. Yeah, and simple number crossing. It's important. It must be simple number crossing.
Why?
So the example of Langer shows. I mean, you can take P2 and the collection of lines, all FP lines, and then using example of Langer, you can show that this pair does not live to the second Witt vectors.
Yeah, that this is not globally. This is not globally.
Yeah. But if you assume.
But the question is, do you have something like for singular pairs? So you have like.
My problem is difficult. I mean, the problem is that when we work with abstractions, I mean, with liftability of pairs, we usually want to assume that something is SNC. So all those, yeah. I mean, so I don't know what happens for in the singular.
You can try it.
Yeah. But if you assume, I mean, if we don't assume anything about the coefficients, then it's not true, because you can take Langer's example and take 1 over p, sum of all FP lines. But yeah, if. Yeah, okay. Okay, so I take a smooth curve, C, and I say it's globally F-split, if and only if the genus of C is equal to 0, or the genus of C is equal to 1, and C is ordinary. And then in the genus C, so in the P1 case, this is globally F-regular. And this case is never globally F-regular. So it's exactly the same as the classification of log Fano and log Calabi-Yau pairs, apart from the fact that in the elliptic setting, we need to add certain arithmetic condition, which is ordinarity. So what happens for pairs? So let us take P1 and delta, and let us assume that the coefficients of delta are contained in the set 1 minus 1 over n, where n is natural. And so this is a set of standard coefficients. It's important by rational geometry, because when we do adjunction, then the set of coefficients will belong to this set. And what happens is that this is globally F-regular if p is greater than 5. And in the surface setting, if we take X to be a KLT surface, this is locally F-regular, strongly F-regular, also if p is greater than 5. So in the surface case, when I had these diagrams, so really we have in the row here this is those are equivalent when the characteristic is greater than 5. And this is a base for Hakon's and Shu work. So in
Last one.
Hara, yes. And I think this is Watanabe, I think, who proved. Yeah? Sorry. So in the Hakon-Shu, there is a slightly different context. It's like a relative context, but it's more or less the same. This 5 really that pops out in the minimal model program. So that's a base. That's a base for the minimal model program, really, for threefolds. So if you would like to generalize the minimal model program for higher dimensions, you'd really generalize those facts. If we could generalize those facts, then plus, of course, a lot of other work, we could try doing something in higher dimensions. But somehow without this, there's no chance of doing anything with the methods that we have right now, at least as far as I know. So, a natural question to ask is the following. Question. We have x delta with the coefficients in the standard set. And now, the generalization of P1 in this context would be exactly a log-del-Pezzo pair. So minus kx plus delta is ample and x delta is KLT. And we ask whether this is globally F-regular if P is large enough. So there exists some big prime number, I don't know, 17, such that this holds. And this is a bit technical because of the standard set, but we have another question, maybe this is more natural. We take x to be a KLT threefold, and we ask whether it is locally F-regular if P is big enough.
I mean, the point is, each of these, for any given example of one of these, it holds for large enough primes.
Yeah, so of course I should rephrase it. There exists prime number. Yeah, uniform P. Yeah, there exists P0 such that then is greater than P. I mean, I say 17. I don't know.
Yeah.
Or yeah. I will state it in a precise way in a moment. So maybe I should say. So all the point in the minimal model program is that we always want to apply vanishing theorems, and we don't have them apart from very special cases in positive characteristic. So that's why we need those F-splittings. So those F-splittings, they work as a replacement of vanishing theorems. And this somehow, those properties work as the building blocks for surjectivity of certain maps. Okay, so let me give the answer to this question. The answer, unfortunately, is no. So you have the following theorem by Cascini, Tanaka, myself. So for every prime P, there exists a KLT del-Pezzo X in characteristic P, which is not globally F-split, and a canonical threefold X also in characteristic P, not locally F-split, F pure. So I should say that here we have an implication that always F-regularity implies F-splitness. So in particular we get that in those two contexts, those pairs are not F-regular. So not only the answer is no, but also we do not need to assume anything about delta. So we can take delta equals to 0 and construct a counterexample. And also we do not need to assume that singularities are in general KLT. There's even a counterexample for a canonical threefold. So it's pretty sad. Okay, so in a certain way, I mean, I don't want to say maybe too much. I mean, I'm not, yeah, I mean, but in a certain way, I mean, at least as of now, it looks a bit like the result of Hakon and Shu is a certain way a miracle. It really uses a certain fact that is really, really dependent on low dimensional theorems. So yeah, I mean, it's extremely beautiful. But somehow we need something new technique really to go forward. At least as far as I understand, I don't know.
Things you can lift or
those examples. So yeah, I will talk about this exactly about the liftability of those. I mean, not about maybe the singularity, but I think it should be. It should be. Yeah. Anyway, so we can can say something about it. I mean, the point is somehow, I mean, not maybe in the singular case. For the singularity is really bad. There are a lot of, so when one finds one, you can see a lot of them. But this property, those KLT del Pezzo X and characteristic P, which are not globally split, they are very rare. So in a certain way, we can recover some properties of them by studying this global F-splitness. So you have the following theorem. It's Cascini, Tanaka, myself. So we say that there exists P0, a natural number, such that every KLT del Pezzo X over an algebraically closed field of characteristic greater than this P0 satisfies one of the following two conditions. So is globally F-regular, but we know it cannot happen always because of those counterexamples. Or now we say that there exists pi x overline to x, which is a resolution of singularities, such that x bar and the exceptional locus of pi lifts to the second Witt vectors. So this is a slightly technical notion, but let me say that this is stronger, it's much stronger than just liftability of the singular surface X. At least right now this is what we need. This kind of liftability we need to get some vanishing theorems. So let me say either is globally F-regular or there exists a resolution such that the exceptional locus together with our smooth model lifts the second Witt vectors. What we really show is that we show something stronger. We show that it lifts to characteristic 0 without ramifications. So it's really like characteristic 0 case, but yeah, I mean, I don't want to define too many notions in this talk. It's a surface, so it's always log resolution, any resolutions. The minimal resolution is a log resolution.
No. Oh, there's no boundary.
There's no boundary here.
No. I mean, there's a cuspidal P1, in which case it's not a log resolution. It's normal crossing, but not simple normal crossing. The exception is set.
Okay, I mean, it doesn't matter. We say there exists a log resolution. I should say, yeah. We show that there exists a log resolution. Okay. So we have the following corollary from this. Okay, maybe one more remark. This holds very often. I want to say usually, but it really holds that this is the main case and this holds in a very special case. And that's the idea of the proof, really. We try to prove global F-regularity in those special cases where our proof fails. We say, oh, but this is a very controllable family, so we can show liftability. Okay, so we get the following corollary. So if x delta is log del Pezzo, over an algebraically closed field of characteristic greater than P0, where P0 is the same P0 we have in that theorem, then Kawamata-Viehweg vanishing holds for any KLT x delta prime. So we do not assume that this is log del Pezzo. So when you have a surface of log del Pezzo type, then Kawamata-Viehweg vanishing holds for arbitrary pairs without any assumptions on them. So at least the question whether Kawamata-Viehweg vanishing holds all rational surfaces, we answer this for surfaces of log-del-Pezzo type in large characteristic. Okay, let me make a few remarks. No, we have no idea. I mean, you'll see from the proof that it's like there exists a number, but I mean, yeah, there's no chances. I think. I mean, we tried, but I think, yeah. Okay, so like you say, I should say there exists an example in characteristic 2, such that A and B, neither A nor B holds. So we really need this P0. We don't know whether we need such a huge P0, but at least this P0 must be greater than 2. And I think we have also an idea of a P0 equals to 3. But I don't know, maybe there is a way of controlling this P0, we do not know. I should also say that this theorem too, it holds for arbitrary x delta log del Pezzo. So we do not assume, I should maybe say, I don't know what I've written. Yeah. So we do not need to assume that the boundary is empty, but the drawback in this context is that this number P0, it depends on the set of coefficients. So we fix some I, a finite set, and now this P0 depends on this I to which coefficients of delta belong. So when we fix the finite set of coefficients, there exists P0 depending only on this set, such that this theorem too holds. And then, yeah, then we have really log resolution now.
And
so sorry,
that's not just coming from the proof, right? You actually have examples where if you vary the coefficients. I guess this, yeah. Okay.
Yeah, I mean, so, yeah, I mean there are examples. So because using Langer's example, you can cook up many examples where we really need that the set of coefficients is finite. I mean, the Langer's examples, you take 1 over p of the sum of all lines, yeah, and this won't lift. But yeah, but p will depend on will change, so it's not a finite set.
So sorry, right?
Sure.
So for KRT you are right. So for KRT the minimal resolution is a log resolution.
Ah, okay.
For log canonical it's not true anymore.
Okay. I was scared because I thought I stopped understanding birational geometry. Anyway. Okay, I mean the last remark, I mean in this context I really need to mention, I mean the following theorem, a beautiful theorem by Cascini Gongio. And it's slightly technical, but I mean it's really, I mean no, it's really nice. If you understand all the technicalities behind it, but it's, yeah, I mean it's very nice theorem. Okay, so now we said I, and it's the motivation really for all our work. So we said I is a finite subset of 0, 1, and we take gamma to be the hyperstandard set of I. So I do not want to define this, but for I equals to I being empty, this is just a set of standard coefficients. And now they prove that there exists P of I such that every KLT surface pair x delta with coefficients of delta in this set gamma is, and the characteristic greater than P of I, and this is locally F-regular. Is locally F-regular. And they also show you have P1 and delta, then it's globally F-regular in big characteristic. So now it's natural to ask, do we really need those two conditions, A and B? So maybe I'll talk a bit about work in progress, which I believe is true, but I do not guarantee that there are no mistakes in that. But I think it's important maybe to mention this context since I may get a question about it later on. So this is work in progress. So I claim the following. I claim that A always implies B in theorem 2. Only liftability to second Witt vectors. I do not claim that liftability to characteristic 0 is implied. So in other words, we always get that there exists this resolution which lift. Moreover, we can really rephrase it in a maybe slightly more concise way, in more general. This is work in progress. So XKLT projective surface Kx not pseudo-effective. So for example, X has canonical singularities. And characteristic of K is greater than our constant P0, which is defined there, then there exists this resolution such that X bar exceptional of pi lifts. So in other words, the main theorem holds even for just KLT projective, sorry, rational, of course. No, is assumed in. No, I want to assume rational. Pardon me?
So what's the singularity of
We are assuming KLT. Yeah. Oh, sorry. For example. So I assume that Kx is not pseudo-effective. So for example, X has canonical singularities. I mean, you may have KLT rational surface which is of general type. So yeah,
Is there a bar somewhere?
Pardon me?
Bar?
No. Is something wrong? There's a bar here, right? I mean, is it okay? Sorry, there exists. Sorry. Though I must say, I mean, in this way, I mean, what's really maybe important, I mean, the possible applications of this. So in this way, we lose really what might be the possible applications that in many contexts by rational geometry, you take an adjunction to lower dimension. And somehow, I mean, we don't have an example, but possibly one could try showing that this case B never occurs in the context one considers. And then one could use global F-regularity and say something for dimension 3. But of course, it's very far-fetched. Okay. So let me give a brief sketch of the proof. So idea. So how to prove that something is globally F-split? So what one could use a global adjunction, which works very similar to adjunction in standard birational geometry. So let me talk quickly about it. The global F adjunction. I mean, I here assume that everything is dimension 2. But it possibly can be generalized higher, at least dimension 3. Okay. We take X, S plus B, a projective log canonical pair where S is prime and S is not contained in the support of B. And now we assume that minus Kx plus S plus B is ample, or one could even assume it's Nef, but then there are some technical issues. And we assume that SBS is globally F-split, where SBS is defined by adjunction. So we have Kx plus S plus B. So maybe I assume here S is normal. So we really do not need to use some adjunction result. So restrict to S, and this we define as Ks plus Bs. And plus some technical assumptions about index not being divisible by p and things like that. And then I claim that x s plus b is globally f split. So what you see, I mean, we assume that this is a log canonical pair, and we assume that it's a good candidate for being globally f split because of the geometric assumptions I gave. And then together with somehow the low dimensional case for the coefficient 1 in the boundary, that this is globally f split, we get global f splitness of x with s plus b. So even if you're interested only in the global f splitness of x, you somehow can cook up this s plus b in order to prove global f splitness of x. Okay, so now I can present the idea. So this is motivated by so-called hunt, or also known as hunt for bananas, introduced by McKern and Kiel. So idea of a proof is hunt, motivated by hunt. Okay, so first we choose epsilon, which is very, very small. And now, if x is epsilon KLT, so x is our, let me recall what I'm proving. I want to prove that there exists P0 such that for KLT del Pezzo pairs in characteristic greater than P0, either they are globally F-regular or there is some liftability condition. So then, it belongs to a bounded family over spec z. So it's like boundedness of epsilon KLT log del Pezzo, but it also one can show it holds in mixed characteristic. And this really implies that there exists P epsilon such that, depending only on this epsilon, such that if the characteristic is greater than P epsilon, then both A and B holds. So the idea is that we have a bounded family, so somehow exceptional behavior happens only in small characteristic. So somehow the logic should be that this P epsilon occurs here, right? But I hope you understand what I mean. Okay, so now is the key point. What happens if x is not epsilon KLT? I mean, we really cannot apply this idea always, because if we take epsilon smaller and smaller, this P epsilon may be bigger and bigger, so it won't be a universal number. Okay, so what happens here? So here, then, in this context, we extract a divisor E via some morphism f y goes to x, and we write pullback of kx is ky plus ae, and this is it will be a divisor with the minimal log discrepancy. So you'll get that a is between 1 minus epsilon and 1. Okay. I mean, now one can show that it's enough to show that just y is globally f-split. I mean, really want F-regularity, but we can simplify it to F-splitness, and somehow, if a variety y is globally F-split, then via push forwarding this F-splitness, one can get it on X. So it's enough to show that y is globally F-split. But now we know that y, AE, and this is KLT, by definition. And now we really use that epsilon is small. So we say that for the ACC, for log canonical threshold, since A is between 1 minus epsilon and 1, and epsilon is very, very small, this implies that y e is log canonical. So somehow we obtained a nice pair when we have a divisor of coefficient 1, which is log canonical. It's a good candidate for applying global F adjunction. Okay, so we have two cases. If minus ky plus e is ample, then we are done by F adjunction. And if is not ample, is not nev, is not ample, then we run an MMP to make this ample. And on the way, we really preserve global F splitness. I mean, it's enough to show that the end result of this MMP is globally F split. And then really, so I should say that the main problem where our proof fails is when this ky plus e, either in the beginning or at the end of this MMP, is equivalent to 0. But somehow such pairs, one can show that they are bounded. So all those examples constructed in B, they are constructed from a bounded family, and then by reversing the minimal model program. But we can do this over the ring V. We can somehow lift to characteristic 0 and reverse the process in characteristic 0. That's why they are liftable. And before finishing, let me say that, I mean, it's a natural question to ask, what happens if a singularity is terminal? Is it F-regular in higher characteristic? And I mean, we do not know. Thank you very much for listening to my talk.
Any questions or comments?
So can you expect the implication of A to B for higher dimensional cases?
So this is a question I was interested in. So if I understand you correctly, you ask, let me clear it. If X is globally F split, does there exist a resolution such that X an exceptional is liftable? Is it what you ask? So I have no idea. So the main problem are terminal singularities. So if there were no terminal singularities somehow, then this would be true. But the problem is, so I mean, in dimension 2 is very easy to prove, right? Because you write pullback of kx is equal to kx plus tilde, where tilde is effective. So then you get by standard arguments that x tilde is globally F split, and then by those liftability properties I mentioned before, you get that it's this whole pair lifts. But in higher dimensions, we have that this might be negative. So I mean, I don't know how. I mean, I was thinking about it, and it's one of, yeah. But at this moment, I don't know how to attack it.
Any other questions? Would you have to speak again?